Probably most of you did not realize that Dr. Hall was an international man of mystery back in the days that he had hair. And I don't know how he got himself into it, but he wound up in an alligator pit of Dr. Evil, and he needed to escape. And as you guys are probably familiar, Dr. Evil does have needlessly complicated mechanisms to do all kinds of different things. And so Dr. Hall grabbed a hold of a massless rope that was connected to that mechanism. For those of you who want to know where to get massless rope, you get it at the same place where you get frictionless bearings. So I think he got both of those at the Ideal Physics store. So anyway, right now where we see Dr. Hall, he is pulling down on the rope with 190 pounds of force. And not only that, somehow he knows the weight of beam AC is 180 pounds. It's rigidly bolted to gear B. And then beam DEG weighs 130 pounds, and it's rigidly bolted to gear G. We also know that gear G has 63 teeth. And so let me write that on here real quick. So this has 63 teeth. Okay. And somewhere else, gear B has 110 teeth. Okay. All right. And so given all this information and that we have the dimensions A, B, C, D, H1, H2, and W, those are all listed down below that figure right there. What we need to do is figure out how much force is carried in the massless rope that extends from point A to point D. Okay? So where would you like to start with this problem? Free body diagram, I like that. Of what? Okay. So where do you know something, right? A lot of times what you need to do with these bigger, seemingly more complicated problems, you need to figure out, where do I know something? Okay? Because it looks to me like for this problem, you probably don't know a whole lot yet about all the forces that act on maybe the gear B and the beam attached to it, or gear G and the beam attached to that. You probably have a lot of things you don't know yet about that. Okay? But there might be a place where you know enough things that you can make some forward progress on the problem. Like, where do you think I might be thinking? You know how hard he's pulling down at point H. And that means that we should be able to essentially do a little free body diagram of this little point right here. That, think of it as being sort of the little chunk of rope that his hand is wrapped around, right? And we can do a little free body diagram of just that piece. So I'm going to do that right down here. That's the little chunk of rope that his hand is holding on to. What sorts of forces act on that little chunk of rope? Okay, we have the weight coming down because Dr. Hall is pulling down there on point H. How hard is he pulling? 190 pounds. Okay. What other forces act on that little chunk of rope? Okay, you've got a tension on the rope that extends. Which one should we do first? Because you've got two different segments of rope. Which one do you want to do first? The left one. So you've got a little piece of rope that comes out there, and we don't know the amount of tension yet in that chunk of rope. So what I'll do is I'll just name it T. It looks like that's E right there, so TEH. Okay. What other force might I have on that point? Okay. Got this other tension coming from this other rope. I'll call that TCH. Okay, so there's the beginnings of a free body diagram. What do I need to do to finish it off? Okay, think about our steps, right? Probably at this stage we want to think about a coordinate system, right? A reference frame to put on this. So we'll put an axis up like this and an axis out like this, where we have X and we have Y. Okay, then what? I don't have quite everything I need on this diagram to be able to write equilibrium equations just yet. So what should I do? Okay, some way of knowing the direction of the two forces in the two ropes, TCH and TEH. And the way that I like to do that for a problem like this, because it's the most direct, is I like to specify the slope. And you can see this is most direct because I'm given a lot of the just linear dimensions of how to know, how far it is both horizontally and vertically from one attachment point to another point of interest on the same figure, right? So let's do that maybe for TEH first. Okay, so for TEH, how far does that rope rise and how far does it run to go from point H up to point E? Okay, H2 is right here, 2.8 feet. So I can put this in as 2.8 of rise. Okay, that's H2. And then what for run? Okay, you kind of see this dimension D right here. D is 4.5 feet, so I'll say this is 4.5 right here. And that gives me enough information to specify the direction of that force. Now what about TCH? How far does it run? Maybe I'll do that one first. Okay, W is 8.7 feet. Since they are both feet, I can just leave them unitless because it's for every foot of run. Since they're all in feet, it's also foot of rise. So I can just leave it unitless for these slope indicators. How much rise would I have there? Okay, that would be H2 plus H1, right, to go from H up to C. Okay, so 5.2 plus 2.8 would give me a total of 8 feet of rise. Okay, and what I have here is a complete free body diagram for point H. All right, what do I do with a diagram like this? Okay, this is the FBD. Over here we do equilibrium equations. Okay, like what? What equilibrium equations might be interesting to us here? Okay, summing forces in the x direction. I'll take rightward to be positive. And what forces do I have that would make, positive or rightward or leftward x direction contributions? Okay, the x components of the two tensions, TEH and TCH. Okay, so what I need to do, I'll start with TEH. But I don't want the entire TEH, I just want the horizontal component. So how do I pick off just the horizontal component? The quickest way to do that, and a lot of you might want to find like an angle and then take a trig function of that angle. You can do that, there's no problem with that, but there's a quicker way. The quicker way is to understand that this is a little triangle right here, where if I take the horizontal component there, 4.5, and divide by 4.5, put that in a numerator, and divide it by essentially what is the little hypotenuse of that triangle, that gives me the same thing as taking the cosine of the angle that force is applied at. Okay? So if I do this and I take the square root down here of 2.8 squared plus 4.5 squared, it's kind of a shortcut that allows me to pick off just the horizontal component of TEH without having to do a bunch of trig functions. Okay? All right, then what? Do I have any other forces that have horizontal components? Okay, TCH. By the way, before I move on from TEH, does it point left or right generally? Left. So I probably should have put a negative sign here because I'm taking rightward to be positive. So here I'll do plus TCH. And how do I pick off just the horizontal component of TCH? Okay, just like I did on the last one, I take the horizontal piece of this little triangle, and I divide by basically the hypotenuse of that triangle, the length of that hypotenuse. The length of that hypotenuse is going to be 8.7 squared plus 8 squared. And those appear to be both of the components that I would need in the horizontal direction. What about the vertical direction? Okay, first of all, let me establish upward as positive. All right, do I still have a component caused by TEH? Okay, but it's not all of TEH, right? It's just the vertical component, and so to get that, I would pick off just the vertical part of this little slope indicator triangle and divide by the hypotenuse of that slope indicator triangle. So I do 2.8 divided by square root of 2.8 squared plus 4.5 squared. Okay. Now, since I kind of messed it up on the last one and didn't talk about the sign early enough, let's think about it right now for this one. Did I get the sign correct for that contribution? Okay, it does generally point upward, and so yes, I do have a positive value there. All right, what about TCH? Positive for that too, right? Tends to point upward, so I'm going to put in TCH. I want just the vertical component, so I'll take the vertical part of that slope indicator triangle and divide by the hypotenuse of that slope indicator triangle. All right. Is that it in the vertical direction? Not quite. What else do I need? Okay, I also have this 190 pounds pointing downward. So I would subtract 190 pounds, okay? And I think that does take care of everything, so I'll set that equal to 0. So once I have this system of equations, what's next? Okay, I might have a calculator available to me that might be able to do a 2x2 system of equations, linear equations like this one. So I pull that out and I pick the 2x2 system there and I put in my coefficients. So the first one I have there will be negative 4.5 divided by the square root of 2.8 squared plus 4.5 squared. Okay, I think that takes care of that coefficient. So I just did the first coefficient in the first equation. The next coefficient is for TCH, so I put that in as 8.7 divided by the square root of 8.7 squared plus 8 squared. Okay, and that one is positive, so I did that right. The constant term that's not a coefficient of either of the variables that we're solving for is just 0 for this one, so I leave a 0 there. And now I'm to my second equation. So my first coefficient for the second equation is 2.8 divided by the square root of 2.8 squared plus 4.5 squared. Okay, and that is positive. So the next entry that I have there is going to be my coefficient of TCH in the second equation. So 8 divided by the square root of 8.7 squared plus 8 squared. That one is also positive. And now we're to the constant term that's not associated with either of the variables, which is it's 190 pounds if it's on the left side of the equation, but keep in mind the way this calculator wants you to enter that term is on the right side of the equation. So what do I do instead of a negative 190 pounds? You go with a positive 190 pounds. And that gives me all of my entries for this system. When I hit equals, it will tell me what the values are. So I end up with 145.14 for TEH. Okay, that would be in pounds. And TCH is going to be equal to 167.42. And all this was a great warm-up for the rest of the problem, right? What's nice is now that we have these two tensions that happen at point H, since the rope is massless, that gives us the same tensions that we're going to have occurring at E and at C, right? So the one that's TEH, that's the tension that will occur at E. TCH, that's the tension that will occur at C. So that gives us what we need to enter the second part of the problem. All right, and that's what I will do at this time. So we'll slide all this down and keep in mind, actually you might help me out, this was 145, so TEH was 145 point what? 0.14 pounds, and TCH was equal to 167.42 pounds. All right, so far so good. Let's keep our eyes on the prize. We need to find the force carried in massless rope AD. How do we get there? Probably the answer is a free body diagram, right? What free body diagram or diagrams should we draw next? Okay. We probably need to think about these beams and look at the beams. It says that they are rigidly bolted to their respective gears. So I have a suggestion. Why don't we, since they're already rigidly bolted to each other, let's treat the entire upper beam along with its gear as a body, and let's treat the lower beam along with its gear as another body. And we'll do those two free body diagrams. Which one would you like to do first? Bottom one first, okay. So let's look at that bottom one. I'm going to do a reasonably accurate free body diagram here. Something like this. Okay, and I have a pin right there in the middle of that gear. What sorts of influences act on this body? Forces. Okay, yeah, we just found this tension, right? So there's a tension that might be acting right here, and we said that was 145.14 pounds. Okay. We also know something more about the direction of that force too, right? What's the direction? Okay, it rises by H2, so it rises by 2.8 and has a run of what? 4.5? So that allows us to remember the direction that that force acted. What else?
The rope bar.
Okay, we have this rope. There's a tension in this rope AD, so I'm going to call that TAD. Okay, what else? Okay, up here, does it give us a piece of information? It says beam DEG weighs 130 pounds. Okay, so that means we probably need to take into account the weight of that beam, and it actually does tell us here somewhere. Yeah, the centers of gravity for each beam are located at their respective midpoints. Okay, So that allows me to know where exactly that force is acting along beam DEG. Okay? So I'm going to go ahead and say that's 130 pounds that acts right there. What other forces act on this body? What happens at a pin? So pin G. You got reaction forces, right? So we have maybe a Y component of reaction and an X component of reaction. I'll call this RGY and this RGX. Okay? What else? Any other forces that act on this? What about moments or torques? What do you think? Okay, yeah, so if you actually look right here, there's an interface with another gear. And there's actually multiple ways we can model that interface. I'm going to show you a way here how to do that that basically mirrors how we've studied gears to this point. So we've talked about how torques get transmitted from one gear to another, and I'm going to show you how this might work between these two gears. Yes, ma'am? So I think basically we're saying they aren't spinning, all right, yet they are still responsible for carrying torque. So they might be sitting still, but that doesn't mean they can't be transmitting torque between one and the other. So the question was, you know, how would it spin? And the answer is it's not likely that this mechanism would be spinning. You know, it's probably sitting still. All right, so what I'm going to show you here is that torque that would happen right there at that interface, we may not know what direction it goes, but I'm just going to assume that it goes a direction. I'm going to pretend like I know that the torque transmitted into gear G is this torque that's applied around the pin, right? And I'm going to name it maybe TG. Okay. And I think that more or less takes care of all of the different influences that would happen on a body like this. What else should I have on my diagram? Okay, yeah, I should have probably a reference frame as well as dimensions. So what dimensions might I need? Okay. So this is a good time actually for us to kind of think ahead in the problem a little bit and think about, we're ultimately going to write some equilibrium equations out of this body. And think about what is a way that I could eliminate some things that I don't know out of my resulting equations. And you want to even eliminate the things you don't know that you don't care about, right? So you don't necessarily want to eliminate TAD from your different variables that you solve for, because that's actually something you want to find. What might we want to eliminate instead? Yeah, RGY and RGX are not interesting to us because we're not asked about them in the problem. And so if I eliminate those, it won't necessarily harm me, and if I can get away with that and not do more equations, then that's good. So if that's the point around which I will sum moments, right? Because when you sum moments, if you choose a point where you have a large number of lines of action that intersect at a particular point, that allows you to eliminate those variables that would intersect at that point, right? So what I'm saying is point G looks very interesting to me as a place to center this, and that means I probably want to say what all of my dimensions are relative to that point. Okay, so let me start putting those in here. So one of the dimensions might be how far is it from G out to point D. Do you agree with that? So like this dimension right here. How far is that? Okay. You've got 4.5 is dimension D, and then C is 4.9. Okay. So that gives me what? Okay, 9.4 feet. Okay, what else might be interesting? Okay, point G to point E. Okay, so that dimension right there, how far is that? Okay, that's just D, and that would just be 4.5 feet. Okay, what else might be interesting? To the midpoint, okay? And the midpoint is just half of 9.4 feet, right? I'll put that one down here. Maybe something like this. Okay, so what's half of 9.4? 4.6? No, 4.7. 4.7 feet. Okay, so far so good. Is that everything that I need? Yeah, so because I will have a horizontal component of force due to this 145.14 pound force, and that horizontal component won't pass through an axis that goes through G, that will create a rotational tendency around G too, right? So what I also need here is how far is it downward from point G down to where that horizontal component of the 145.14 force is going to act. So how far is that? Okay, that's this dimension A, which is 1.4 feet. All right, so there is a reasonably complete free body diagram. What should I do with it? What do we always do with free body diagrams? Okay, we might want to write equilibrium equations, and specifically one that I'm pretty sure I want to write is the moment equation around point G. I kind of explained a second ago that that's a nice equation we might be able to use to eliminate a couple of the variables we don't know. So I'm going to go ahead and do that one first here. Some moments around point G. Okay? So what do we have that contributes to that? TAD, right? Times what? Because it needs to have a length associated with that force in order for it to be a moment. 9.4 feet. Okay. And what direction should I be summing moments? It doesn't really matter, but we need to probably pick a direction. Okay. Let's say counterclockwise, and if that's the case, how should I count TAD? Probably as a negative value here, right? Because it's clockwise instead of counterclockwise. Okay, good so far. What else creates a tendency to rotate around point G? Okay, the weight of the beam certainly does. Let's think, is there anything unknown that would create a tendency to rotate around point G? Okay, TG creates a counterclockwise tendency to rotate around G. So I say plus TG. TG does not need to be multiplied by any length because it is already a torque, right? So I don't need to multiply it by a length to make it into a moment or torque. All right, someone mentioned a second ago the weight of the beam. I agree with that. So let's add that in down here. Let's say there's a counterclockwise tendency to rotate of 130 pounds times what? 4.7 feet. Then what? Okay. to this I'm going to add 145.14 pounds. Let me start with just the vertical component. I'll start with a vertical component. And so if I do that, I need this times 2.8 over the square root of 2.8 squared plus 4.5 squared. Okay. So far, what I've done is I've picked off just the vertical component of the force acting at E. What do I need to multiply this by to turn it into a moment? Take your vertical component and multiply it by what? Horizontal length, right? So my horizontal length is 4.5 feet. Right? See that horizontal length right there? But then I need to also think about the horizontal component of force acting at location E and multiply it by what? The vertical length. Okay? So I'm going to add to this. Okay, that's also going to be a counterclockwise, so I will add 145.14 pounds times 4.5 over the square root of 2.8 squared plus 4.5 squared. And this multiplied by what? 1.4 feet. Okay, so far I've handled TAD, TG, the weight of the beam, and the force in the rope, rope EH. Okay, do I need to handle RGY or RGX? Okay, not for this equation. All right, this equation, those two are eliminated because I'm summing around point G. Okay, so this is that whole equation. How many things in that equation do I not know? Okay, there's two things I don't know, TAD and TG, which means I can't solve it just yet. Not only that, if I add a force equation in the X, that adds an unknown, right? Because it'll add TG or RGX, excuse me. And if I add my Y equation, that adds another unknown, RGY. So neither of those directly help me to be able to solve anything just based on this one diagram. So the next thing I've got to do is think about, do I have another diagram that I could use in conjunction with this one that would help me solve the whole system? And what do you think I have in mind? Okay. So doing something similar to what we just did, only now for the top body up there, the gear around B. Okay, or the pin at B. And the beam that's attached to it. All right, so that'll have to suffice for our free body diagram shape. How do we add stuff to this? Okay. So, yeah, what we need to do is make sure that we are consistent whenever we apply the, kind of the things that are common between our two free body diagrams. So, for instance, AD that I have right here. Okay, I called that TAD on the last one. I have to show it equal in magnitude and opposite in direction on this one. So I'll do that and call it TAD. Okay, what else should I put on here as another force? Okay, tension in CH. Okay, that value was 167.42 pounds. And we also, while I'm here, I'll go ahead and indicate that the direction of this is also known. We said that the rise of it was going to be 8 feet, and the run, W, was 8.7 feet. Okay. Then what? Okay, the weight of the beam. Now the weight of the beam happens right in the middle of the beam. And the weight of the beam was 180 pounds. Okay. And then what about the torque happening from the interaction between B and G? Do I know anything about that?
Would you assume it's the opposite direction of the one?
Okay. Question is it the opposite direction of the last torque? And the question is that how torques interact between gears where they are not accelerating? Okay. And you think about it, if you were to apply, since gears basically turn opposite directions, if you apply torque in opposite directions, it would tend to make them accelerate because nothing would cause them to slow down. So really what we want to do when we have two gears interacting like this is we want to assume torque in the same direction because that's ultimately the way the two would interact with each other. Okay, so I'm going to also show a counterclockwise torque on here. And how do I say what the value is of that torque? Do I have anything that would allow me to know the value of torque relative to my last analysis? I have a number of teeth, right? And which gear has more torque? Bigger one or the smaller one? The bigger one. So I would submit to you that the torque on this gear is going to be the torque on the last gear, TG, multiplied by what? Okay. If you look at this, gear B has 110 teeth, gear G has 63 teeth. Gear B probably has more torque because it's the larger gear, and it's larger by the ratio of the number of teeth in the two gears. So if I take TG and multiply it by 110 over 63, that would be the torque that would be felt in that other gear. Does that make sense? Okay. You know, I should probably put these on here also to make it complete. You know, I might have some reactions that would happen at this pin. We'll call this RBY, and this one I'll call RBX. All right, what else should I do here? Okay, it might be worthwhile me setting up a set of axes, something like this. Say that's X, and here I'll call this Y. And what else? Distances. Just like the last one, we cared about that vertical distance. I may as well put that one on here now, right? From the pin up to where all of these forces are applied. What is that length? Okay. That's that B value right there, 1.9 feet. All right, what else? Okay, it looks like C is the distance from point B horizontally back to TAD, or point A back there. So that would be 4.9 feet. Okay. The distance from point B horizontally to point C, that's fairly easy for us to know as well. That's going to be D plus W. So that would be 4.5 feet plus 8.7 feet. All right. That gives us what? 13.2 feet. And what else do we care about? probably need to know where this weight is applied to, right? How do I find that? Okay. You take the total distance, divide by 2. That gives you how far it is to the middle from either end. But then what? You'd want to subtract the 4.9 so that you figure out how far it is from point B to the middle. Okay. So what that ends up being, I'll go ahead and use a calculator for that. Okay. We basically take 4.9 plus 13.2 and divide that by 2 and add 4.9. Okay, 13.95. Did I get that right? Doesn't seem right. Try it again. 4.9 plus 13.2 divided by 2 plus, no, not plus, minus. That may have been my error before. 4.9. There we go. 4.15. Okay, 4.15 is this distance right here, 4.15 feet. And that should be everything that we need to write an equilibrium equation for this body. Okay, I'll do that down below here. Summing moments around point B, where counterclockwise is countered as positive, and I'll start with TAD. Okay, that tends to be a positive, it tends to be a counterclockwise tendency to rotate caused by TAD, so I count it as positive, multiplied by what length? 4.9 feet. Okay, then what? I'm going to do my other variable next. So to this, I'm going to add TG times what? 110 over 63. Okay, what next? Okay, minus 180 times 180 pounds, I should say, times 4.15 feet. Then what? Go down below here and go to minus 167.42 pounds. Okay. I want just the vertical component first, so I'll multiply by 8 over the square root of 8 squared plus 8.7 squared. Multiplied by what? Because I need a length also, right? I picked off the vertical component of the force. It's going to be, that component is going to be a clockwise tendency to rotate, which is why I've got the negative, but I need a length to multiply that vertical component of force by. 13.2 feet. Okay, and then last but not least, I need to take care of the horizontal component of the 167.42. Okay, that horizontal component, if you look at it, it's acting right here. It's going to have a counterclockwise tendency to rotate, so I count that as positive. 167.42 pounds multiplied by 8.7 over the square root of 8 squared plus 8.7 squared. And I multiply this by that height of 1.9 feet. Okay. Is this better? How does this help me now?
Because you have two equations for two unknowns.
Okay, if you look at this, I have two equations where I have two unknowns. TAD, that appears here and here. I also have TG, which appears here and here. Everything else is known, and it's a linear system of equations, and so I can plug these into the calculator, which I already showed you how I did that one time. This is really no different. You just need to make sure that you move those constant terms that aren't associated with one of the variables over to the right-hand side of the equation before you punch them into your calculator. And so in the interest of time, what I'm going to do is give you what the solution is to this system of two equations and two unknowns. It winds up giving you 186.707 pounds for TAD. And it gives you 626.457. I'll just say 0.46. And this will be in foot-pounds. And this is our value for TG. Okay. So we go up and we see if that's one of our choices. Looks like it's close enough to being choice I right there. So I hope we're happy that we have helped out Dr. Hall, or maybe we helped him out. That's the kind of thing he would probably wonder about as he's hanging above an alligator pit. So now he does not have to wonder how much tension is in rope AD.